Some introduction because the audience is general. So in structural biology, which is a very hot topic also these days for understanding how coronavirus affects humans, we don't work with natural proteins. We express them in bacteria, usually E. coli. After expression, you obtain a family of expressed proteins. So one needs to isolate the protein you want to study. And we do that via liquid chromatography. And what you see here is an electrophoresis gel, which verifies that we isolated the specific protein we want to study. The solution has to be very pure, otherwise it doesn't crystallize usually. So after we isolate the protein, we crystallize it, and there is a lot of physical chemistry behind protein crystallization. That's why it developed to a separate field, scientific field, in fact. The most successful technique is single crystal X-ray diffraction, and it will always be. After we collect our data based on a single crystal of good quality, we solve the phase problem, and here is where crystallography begins. We need to solve the structure, produce electron density maps, and based on the maps, we refine our structure, and finally, we deposit our model to the protein data bank, where a group of experts runs a set of stereogeometrical software to verify its precision. So our idea was to replace this data with this data. These are powder diffraction data. The difference is that our sample is not a single crystal, but many crystals which are randomly oriented. And therefore, owing to Bragg's law, instead of single reflections, we have co-centered rings that then we integrate the intensity around each ring, and we produce these nice two-dimensional profiles. On the vertical axis, it's the diffracting intensity. On the horizontal is the 2 theta diffracting angle. After we extract the intensities from these profiles, the programs do not recognize whether you did a single crystal or a powder experiment. And this is important because we didn't have to rediscover the wheel. Crystallography is the same and programs are similar. So we extract the intensities, we produce electron density maps, and finally our models. So the successful and recognized methods in structural biology for amorphous samples which look like this, we use NMR. These samples are not crystalline, are in solution. NMR is successful for smaller proteins, lower than 100 kilodalton often. SAX, SANS, or cryo-EM for larger molecules, even viruses these days. For good quality single crystals, the best technique and the most precise technique is single crystal diffraction and crystallography. Usual requirement is to have a crystal of in size 10 microns or even smaller these days at microfocus beam lengths. However, the problems with this technique, one of the difficulties is to obtain the nice single crystal. So back in 2003, we thought, why not apply powder diffraction, which is a very common technique in material science, in order to look at samples which look like this. These samples sometimes under the microscope look amorphous, but they are not, in fact. They are consisted by crystals which range in sizes between 100 nanometers and 10 microns. And this is why we explore this method initially to study nanocrystalline protein precipitates, which are more often formed even by accident without trying too much. But the method has other advantages. Also, we can study twinned samples, which is a typical problem in protein crystallography. We can do very quickly and very well high throughput crystal screening in order to optimize crystallization conditions, for example. We study the protein structures at various crystallization conditions. This is a tendency, again, from the material science world. We want to see not only the structure of a protein molecule at a specific set of conditions, but to observe also how the protein structures behave upon variation of their physicochemical environment or biochemical environment. More recently, we started observing in situ processes like chemical reactions. And of course, in order to produce nanocrystalline precipitate is much easier. So we use less chemical additives during crystallization, which is critical for the pharmaceutical industry. So we work with many different morphologies of crystals. These are needle-shaped crystals of a virus protein domain, nanocrystals, or samples that have larger single crystals, but in this case, we wanted to check the homogeneity of the sample. This is a critical parameter, homogeneity in terms of polymorphs and crystal sizes. It's critical for the development of pharmaceuticals, but it's also critical for performing a successful X-ray free electron laser experiment. So usually what we currently do is powder diffraction prior to X-ray measurements in order to verify that our sample consists of one polymorph and the crystals have the right dimensions and morphologies to ensure higher chances of a successful experiment at XFEL. One example of polymorph, very high throughput polymorph identification from our group corresponds to this case. We have done a lot on insulin, and I will explain why. We co-crystallized insulin with this ligand, which is called 4-ethyl resorcinol, is a ligand of insulin. And we crystallized this compound, this complex, at various pHs. So the pH has a tremendous effect on protein structures because protein molecules are charged molecules. So if we look at 4 out of the 20 prepared samples, already with an optical microscope, we see different crystal morphologies. So we were suspecting that there are phase transitions, polymorphism, basically. We collected data at ID31, ID22, the high resolution powder diffraction beamline at the SRF. And these are plotted, all of our data as a surface. On this axis is the increase in crystallization pH, and even by looking at the data without any analysis, one can see that there is a clear phase transition at pH 5.5 approximately. One way to treat data, hundreds and thousands of data sets without too much effort or any knowledge of crystallography is cluster analysis. So you import all your data, and there are several mathematical models to cluster the data based on their similarities. This is what we did. So we import our data in a program, in this case called HighScore Plus, and the program clusterized the data in 4 different clusters. So we knew that probably we have 4 different polymorphs of insulin with this ligand, which appear with increasing pH. Then we did polyanalysis, which does not require any structural knowledge. This is our ligand. We repeated the experiment twice, and we saw that with increasing pH, we have 1, 2, 3, 4 different forms, 4 different crystal polymorphs, in fact. In the second time we repeated the experiment, we didn't observe this form. This work lasted for approximately 1 week, starting from sample preparation. So within 1 week, we had created a phase diagram, a map, polymorph map for this complex of insulin with the specific ligand. So that's very, very simple to do, even without knowing crystallography. Something I wanted to do since my time at the SRF was diffraction measurements of proteins upon controlled relative humidity variation. In fact, I had seen Trevor Forsyth's from the ILL beautiful work on DNA. Let me remind you that all organics are held together in their three-dimensional conformation via hydrogen bonding, and also in the crystals via hydrogen bonding as well, because the crystals contain a lot of amorphous solvent. So humidity is a very, very critical parameter for protein structures and their function as well. So over the years, we identified the right chamber, which is this one. Anton Parr produces it. We fitted it on our lab diffractometer, and we loaded initially lysozyme microcrystalline samples that you see here. There is a carousel. We can load many, many samples, and we can really collect powder diffraction data upon very, very precisely and controlled variation of relative humidity. This is just a small part of the data we collected during that experiment. It corresponds to tetragonal lysozyme. These are all of our powder data upon decreasing relative humidity. It's like we look at the data from above. So wherever you see color, there is a diffraction peak. And first observation was that below 95% relative humidity, there is an indication for a phase transition. Then we did several more experiments, and we saw that we got two new crystal polymorphs of lysozyme. One is monoclinic with the orange lattice dimensions, and the other is tetragonal, again shown with the orange color, the lattice dimensions. Now, in comparison to the known forms, which are shown in black from the PDB, these have not been observed before and could be observed upon this controlled relative humidity variation. Since then, we've done several more experiments, and most of the proteins show dramatic transitions upon controlling these parameters. So I consider it as a very, very hot parameter for protein crystallography. These were the two first experiments on lysozyme. One paper describes this new monoclinic crystal form, which was later solved via electron diffraction. And the second paper describes our observations on tetragonal lysozyme. I note here that lysozyme is probably silicon for protein crystallography, but even such a well-studied protein can really give surprises, simply because proteins are very flexible. So for today's presentation, I chose three case studies. One peptide drug, which is a component of pharmaceutical out in the market today. The second part corresponds to some observations on insulin, and the third part is structural studies on a specific virus protein domain, as viruses absorb a lot of our attention these days. So this is the peptide we worked on. It's a component of a drug produced by the pharma company CBL. It's a synthetic analog of somatostatin, which is a peptide hormone that regulates the endocrine system. It consists of 8 amino acids. It has a disulfide bridge. And if you notice, there are 2 D amino acids. D amino acids are not abundant in nature, but as this is a synthetic molecule, they added them because it makes the drug more stable. So the only structure which was known was this one by Paul et al. From 1995, and we wanted to revisit the structure in order to determine it in higher resolution, higher accuracy. We thought it would be easy, but crystallization of the compound was not, in fact. Whatever we did, we were always getting crystals which look like this or like this. These stuff are perfect for powder diffraction, but are not really good for single crystal diffraction. And therefore, we used samples which look like this in order to collect data. First in our lab, this is our lab diffractometer. It's produced by Panalytical, focusing mirrors here, and a very nice pixel detector, which is located here, really produce high quality data even for these samples, which we didn't expect in the past. So the samples are loaded in glass capillaries. This is the X-ray generator, and the detector moves on top of the 2 theta circle in order to collect the data point by point. And in fact, it's a copy of ID22, which you see here. It's Andy's beamline, Andy Fitch's beamline. Again, our samples are loaded in glass capillaries. The beam comes out this way, hits and transmits the sample, and the diffracted beam, after passing a set of anti-scattering slits, analyzer crystals, more slits, they are collected point by point with these 9 detectors. This arm is moving on top of the 2 theta circle. In fact, we use this instrument quite a lot, and also this instrument at the Swiss light source, which is the same. However, the detector here is called Mythen. It was produced by the detection group at the Swiss light source. And the power of this detector is that it's something between point detector and area detector, so it's very, very fast. And now that I heard by Jean Susini about the Eiger detector, which will be installed at ID22, I'm very, very hopeful that this axis of data collection will be implemented on ID22 as well. So the effect of the instrument is tremendous, of course, and over the years, especially the years I've been working for the ESRF, we did a very exhaustive search on different instruments. You can read more about the instrumental effect on this publication. We collect data in the lab, ESRF, SLS. These are 3 data sets of octreotide. And if we look at 2 peaks, you see that the effect of the instrument. The laboratory diffractometer does not provide so sharp peaks. This we call it angular resolution. However, the synchrotron provides the best angular resolution, the sharpest peaks, and this is critical because peaks, as you can see, overlap. So the sharpest, the better, in order not to lose information. However, in the lab, samples survive for longer, at least 100 times longer to the radiation. So we get better counting statistics in the lab and better angular resolution at the synchrotron. And usually what we do, and in all the examples I'm going to show, we have combined different data sets in order to increase the information content of the data, which is absolutely necessary for solving or refining so complex structures as peptides and proteins, of course. In order to refine our structures, Bob von Driel has produced this nice software called Jesus. He modified it for proteins, for protein data. And a few years ago, he produced a technique to help us refine our complex molecules in a simpler way. So, of course, we use the Rietveld method and a lot of stereochemical restraints. Here you see what is happening on different amino acids during the refinement process. So the flexible rigid body approach means that we consider each amino acid as a rigid body that can move from its origin and can also rotate, but it cannot be distorted. So this approach made our refinements much more robust. It has been implemented in Jesus. It's free of charge, software free of charge, and this is the technique we use in order to refine protein structures. More details are given in this article from 2004. Finally, for octreotide, we got the structure very, very quickly. 2.8 angstroms resolution, again, data from the lab and the synchrotron. And here you see how the molecule looks like as an electrostatic potential representation. Now, more recently, we continued data collection and we collected even better data. You can download our derived model from the PDB. It has this code. The structure has a resolution of 1.87 angstroms. Increasing the resolution from 2.8 to 1.8 is a huge step, actually, because you can really see a lot more details. Going to the second part, why insulin? One might think that is a very, very well-studied protein till Dorothy Hodgkin got her Nobel Prize for her first structures of insulin. In 2004, we were approached by colleagues at Novo Nordisk, Copenhagen, who asked us to do a map of polymorphism. Insulin is very, very highly polymorphic at molecular and crystal level. So we have molecular polymorphs and crystal polymorphs. The interesting thing is that drugs currently in the market sometimes are amorphous, injectable. They are monomers of insulin. The characteristic of these drugs is that they are rapid acting. The activity curve has a peak here within the first 2 hours of injecting the patient. But lots of drugs out in the market are crystalline. And these drugs have a not so quick action, but have a better, a long action. So the patient does not need to be injected too many times per day. So these are some of the drugs currently out in the market. And if you look at these two, or all of these are all crystalline, corresponding to different space groups and lattice dimensions. In 2004, we started this collaboration, which still continues, and we have produced several published results that you see here, and several confidential information. Our role in this project is to try to identify new crystal forms with better activity, in fact. So just a very brief introduction about insulin. Is a small hormone of 6 kilodaltons. Its active form is this monomer. If we look at it, it consists of 2 chains, one shown in red, the other is shown in blue. However, in nature, insulin is found as dimer that you see here, or, let me share the screen again. Apologies, but there was a Microsoft error. Give me just 1 second. Murphy's Law. So while I'm reopening my presentation, I will try to describe. There are 3 main forms of insulin: monomeric, dimeric, or hexameric. The active form is the monomer, but many drugs have dimers or hexamers. So there is a constant search towards different conformations that could be used as drugs, to say it simply. I hope you can see it now. Oh. Apologies for this. Okay. So let's look at it again. So in the dimer, there are 2 chains which are held together via 2 disulfide bridges. In the dimeric and hexameric forms, we have distinct molecular conformations. One is the one shown now, where the part of the blue chain is extended, as shown in this video. This is called T6 molecular conformation. The other one is when this part of the chain is helical, and this is called R6. And there is an intermediate one, which is called T3R3. Here you see how the hexamer is formed. Hexamers are formed in the presence of zinc. Two atoms of zinc located in the center of the hexamer keep this hexamer intact. These were the first structures solved by Dorothy Hodgkin, and you see here the three molecular conformations T6, T3R3, and R6. So this is a very quick introduction to insulin. And this is just one of example of our work, very recent. We used polyphenols as ligands of insulin. There is a constant search of new therapeutics against diabetes. Diabetes became epidemia, basically. So there is a constant search of new drugs having better absorption, distribution, metabolism, excretion, and toxicity. And in this game, we try to co-crystallize insulin with ligands which have a therapeutic effect, like polyphenols. Polyphenols have antimicrobial, anti-inflammatory, anti-cancer, and antioxidant effects. And probably you are aware that oxidative stress is a parameter which is related to many diseases, like Alzheimer's, like diabetes, etc. So we co-crystallized insulin with these two polyphenols, picumaric acid and resveratrol, in a pH range from low to high. In the upper panel, you see 3 samples with this ligand and 3 other samples with this ligand. So again, via optical microscopy, one can really see the polymorphism which is coming up. After collecting lots of data at the ASRF, we saw that for the first polyphenol, we have 3 phases, R3, P21 zeta, and P21 beta, whereas for resveratrol, we have again the same phases appearing at different pHs. Now, the interesting thing is that the P21 zeta and P21 eta were new forms, and especially this one, the P21 zeta, is very interesting as a drug target because the unit cell contains many insulin molecules, very closely packed, and this could be, if it is used as a drug, we could reduce the number of injections to a patient. That's the interesting thing about that. We got a single crystal of this polymorph, P21 zeta, and we performed single crystal diffraction experiments at BESI together with Manfred Weiss, Chris Kosinas, and Jan. And we identified also 3 ligand sites of picumaric acid. In the hexameric form, here is the ligand. More details about this structure are now available in this publication and also from the protein data bank. This is a small part of the phase diagram we've been constructing since 2007 for insulin co-crystallized with different ligands. On this axis are the ligands that you see their stereogeometry here. And on this axis, it's the increasing pH. Look at how polymorphic it is. The crystal form is changing even if we change the pH by 0.2 of a unit. So this was the first shock for a person not familiar with insulin. And the second surprise is that all these phases correspond to the same space group, P21, it's monoclinic. However, as you can see, we denote them with alpha, beta, gamma, delta, zeta, and so on, because they are different crystal forms. These 7 forms were identified by our team, and here you can read more about them. And these 2 forms, one is monoclinic, the other is orthorhombic, were identified by our colleagues at Novo Nordisk, first from powder diffraction and then solved from single crystal techniques. So insulin is a very, very rich phase diagram, has a very rich phase diagram. These are the 7 polymorphs we discovered. It's all the same space group, but completely different lattice dimensions. And the important parameter here is what we call packaging efficiency, which means how many molecules, insulin molecules, are packed in the unit cell. The more, the better, because as I said, if they are used as drugs, the patient gets more insulin with fewer doses of the drug. Another interesting thing corresponds to the P21 gamma polymorph, where we got it upon co-crystallization of insulin with M-cresol. It's a small organic that you see here in pink. We wanted to see if from powder diffraction we could not even refine the protein, but also detect where the ligands are. This is important for the development of therapeutics because sometimes the drug is the ligand, is the small organic molecule. So it's very critical to be able to precisely identify its position and its binding site. In this case, we identified 6 binding sites of this small organic on the insulin surface. They are all hydrophobic. And this result was later on verified via single crystal methods. So the conclusion from this is that we can, with good quality powder diffraction data, you can even detect the ligand sites. As this was the first time we demonstrated that something like that is feasible, it attracted the attention of the SRF. And more can be read in this issue of the SRF News back from 2015. Just to be clear, in our structure refinements, we combine multiple profiles. One data set most commonly is not sufficient. Instead of traditional electron density maps, we use total omit maps, which are slightly different in their philosophy. They contain less model bias, and they are described by BAT in this article. And of course, we use lots of software packages. But as I already mentioned in the beginning, we didn't have to rediscover the wheel. We can use software designed for powder diffraction data, software designed for single crystal data, and some programs were written mainly by Jonathan Wright and Bon von Drill in order to help us to move quicker in our data analysis. All of these are used every time we try to solve and refine a structure. Now, okay, I showed some part of the phase diagram of insulin with these 2 ligands, and we observed these phase transitions with increased pH. However, we wanted to see what is happening on insulin with increasing pH without any ligand. And this is important because the less chemical additives, the better candidate as a drug this can be. So up to here, we observe the common structures that I already mentioned, T6, T3R3, R3, space group. However, when we increase the pH, we get a cubic phase, which we prepared, and then we visited the SRF, and we collected this profile on ID22. The very short story is that that night we put the sample on the diffractometer and we needed some dinner in Grenoble. We come back and we see this beautiful profile, and I was certain that we had mixed up the calibrant and the real sample. However, it's real. Cubic insulin gives data up to 2.7 angstroms resolution, very sharp reflections, very, very beautiful data. However, in powder diffraction, the higher the symmetry, the less the information content of the data, because peaks exactly overlap due to symmetry. So the completeness of the data of this pattern is not very high. It starts from 50% and it goes down with increasing Q range, 1/D. So I wanted to see whether I could refine the structure using this data, and more data were collected in our lab that you see here, really not bad at all. 6 data sets were combined, the FRB approach, the Rietveld method, and of course, stereochemical restraints. This was the easiest refinement I've ever done. And what I hope you will see in this video, this is our electron density map as we extracted it from these profiles, and how a program called WinCut fits the model amino acid by amino acid to the density. If you observe at the density, one can really think that it comes from single crystal diffraction because the quality is very, very high. So sometimes with good data, one can easily solve a structure. The structure is this. Soon it will be available in the PDP, and more details will be provided in a forthcoming publication. I'm passing it quite quickly because I want to show you
Irene, 3 minutes.
3 minutes. Regarding a virus protein, I chose to show a protease coming from a virus called Coxsackie. The protease is in the genome of the virus is here. The virus is shown here, RNA virus. The structure, the protein was isolated, crystallized. I want to go to the important, we did powder diffraction, but I want to go to show you something very, very hot right now, which is called fragment screening. So after we managed to produce the protein and characterize it via powder methods, we isolated a single crystal and we did fragment screening at BESI. Fragment screening is very, very hot even for corona because they soak the crystal in different organic ligands and they very quickly detect potential inhibitors of a protein. In this case, we identified 4, and last week we did 7 more experiments in order to complete this work. More will come up. Fragment screening is a very, very big step forwards in structural biology right now. These are 3 virus protein domains we've worked in Patras, Mayaro, Coxsackie, and Dang. And so by concluding, polymorph identification, crystal size and morphology, and phase mapping are very easy to do. Structure solution via molecular replacement and structure refinement, as well as ligand binding, requires training but are feasible. And of course, the technique is ideal to be used together with X-ray measurements and electron diffraction on single nanocrystals. I will conclude with this. This is a very recent result I'm very, very proud of. It's in collaboration with Dimitris Verg and Lars Redeke. They grew crystals of different viruses, virus proteins in cell. They put the cells directly in the beam at a SAC station at DESY. They collected powder diffraction data and we achieved polymorph identification. So in-cell crystallography is also feasible. And I will leave the acknowledgements for all of you. Thank you very much for your attention.
Thank you very much, Irene. Impressive improvement in all this technique. And now, even at 1.8 angstrom resolution, it's massively impressive. We have one question from the audience. After you have screened all the polymorph, did you try seeding to grow one single crystal?
Yes, and in fact, in certain cases, it worked, and that's how we grew the single crystals to obtain the single crystal data I showed. In certain cases, it works, it speeds up crystallization, and it produces better crystals.
Thank you. And if I may, I would like to ask you just one thing about the insulin. Were zinc always needed for all the hexameric forms, or just the resveratrol or other polyphenol were able to trap the hexameric form?
Yeah. I've seen one ligand which absorbs zinc. I cannot say the name of the ligand right now. In most of the cases, zinc needs to be present, otherwise the hexamer does not is not preserved.
Thank you very much. If there are no more questions, no. Thank you again, and I'll pass the screen to our next speakers and next chair, Alberto Martinelli. The floor is yours. Is Alberto there?
I think we have a break.
It's the coffee break now.
Oh, yeah, sorry. Sorry.
Our coffee break. Yeah.
Yes. So we reconvene at 3:30. Let me thank all the speakers for the wonderful talks. Thank you.
And people can visit the sponsors if they have some time with their coffee.
Thank you.
Special time for the sponsor prize. Yeah.
Thank you.
Yes.